whatever our model, one needs to minimize f of x minus y, where y is the data, the values that you want to predict. You want to minimize the error between what you already have, real values, and your predicted values for those real values. But f is complicated. There is no formula like the normal equations that we had for linear least squares. So all these methods, whether they are regression with logistic functions, support vector machines, neural networks, all learn the parameters through an iterative process. We start with some f, which is a parameterization of the function f. It may not be linear like f transpose x. It could be some other parameterization. So it could be, you could have squares, you could have exponentials, you could have all kinds of things. But you have some parameters which tell you what this function f for each choice of parameters is. And we need to refine it iteratively to find the f which minimizes the error. In the world of neural networks, the first such algorithm was called backpropagation, which has nothing to do with feedback neural networks. It's just the name of the algorithm which iteratively learns f. While in other areas which were probably more mathematically founded, straightforward optimization techniques were used to find the minimum of this error. So if we start off with a guess and we choose maybe a slightly different f as two different guesses, one way to start minimizing this error or moving towards a value of f which is likely to have lower error is to use something called gradient descent. This formula looks a bit daunting, so let me explain it in simple language. Epsilon of f is a function of the parameters of f, so one can measure how fast this function changes if one changes each component of f separately, which is nothing but taking the partial derivative of the function with respect to that component. String all those partial derivatives together and you'll get a vector which is just this del sub f of epsilon. That vector tells you which direction to move each component of f so as to reduce epsilon. So, for example, if the first component of f is such that if you increase it, then epsilon decreases, then you would choose to increase that component of f. If the second component is one which decreases epsilon only if you decrease that component, you would decrease f. So then that particular element of del would be positive. So you'd get this vector del of epsilon computed using your old value of f of f. That means your previous iteration, start with f0 for example, and then subtract some small multiple of this derivative to your current guess to create a new guess. Now, you need to compute these derivatives, so you use the differences between epsilon at f of I and epsilon at f of I minus 1, divide by f of I minus f of I minus 1 component-wise to get estimates for these derivative, and that's why you needed two guesses to start with, so because you have to bootstrap this iteration. Now this is a very popular and very simple method. You can have more complicated ways of finding the minimum value of epsilon by using Newton's iteration, where you use second derivatives in addition to first derivatives, and various different techniques in the mathematics literature are available to you. This works fine if you have numbers. That means if you have the x's are actual values, as we have been assuming, but there are of course some caveats. This iteration sort of works, and all such iterations work provided there's only one minima, and you're actually starting very close to that minima if there are multiple minimas. And if there are many different minimas, you might get stuck in a local minima and not really get to the real minimum value. So you need better techniques. The other thing could be that the function f might not necessarily be parameterized by a single set of values. There may be some constraints. You might have a function which says that you have 5 different lines which meet at the connecting points, and that's your function. So you're going to try to fit 5 lines to all your data. Then you have constraints, which will then make this iteration a little bit more complicated and complex as well. But we won't go into those details right now. The other problem is if x is not numbers, and if x is categorical, at least some of the x are categories like yes, no, red, blue, or green, then you somehow have to convert them to a binary form. So if there are n categorical variables, you might want to convert them to, for example, 0 or 1. Of course, now you're going to have many more than n. So you would say, like words, you have categorical variables which are words, and you suddenly increase the dimension of your space from, say, you're talking about one word, but words could be out of a set of millions, so now you have a million dimensional space, and it's 0 or 1 depending on whether that word is there. Now that tremendously complicates such methods, and they often become unviable if your categorical data is very high dimension, and you have to use different techniques to learn parameters. You could also convert these categorical variables to real numbers through a process of reversed fuzzification, which we won't talk about. But essentially, you think about high, low, and medium as functions which are not fixed as being high, low, or medium, but could vary as something being 50% high, 20% low, etc. And then use such fuzzy membership to convert your categorical variables into real numbers. And then once you have real numbers, you can use these techniques, or you could deal with the space of categorical data itself. And there are techniques like neighborhood search, heuristic AI search, genetic algorithms, and such techniques which don't rely on converting your parameters into real space. And then you get the problem of a combinatorial explosion, and you have to use all kinds of techniques to figure out good ways of minimizing the error. And lastly, as we have seen in previous lectures, probabilistic models can deal with probabilities of variables taking on particular categorical values, as opposed to having to convert those to numbers or deal with them directly. And these techniques are becoming increasingly powerful and popular precisely because you're able to deal with the numbers without having to get into too much exponential or combinatorial blowup. Now, that's quite a mouthful, and many of you might not have got it, but those of you who are on the verge of graduate research might want to listen to that spiel a couple of times, because it does sort of unify different or sort of give a bigger picture of how learning parameters in predictive models work and what are the possible options. There are some more linkages which I'd like to explore. For example, here we are trying to minimize the error in a predictive model. In other situations, we might need to maximize a choice, such as you want to find the best way to transport goods across the country, or the best way to allocate one's advertising funds across different channels. So there you're trying to maximize some function, and that's related closely to the problem of minimizing the prediction error. Similar techniques, gradient descent, Newton's method, and various others apply. All the similar problems in terms of categorical data, local minima, and constraints all apply as well. Then once one has decided where one wants to go, one needs to figure out how to get there. So typically, if you're driving a car, for example, you have a system and your angle of steering could be, say, theta, and every time you change your theta, your car will move in a certain direction, so you'll have a new state of your system, and the goal is to figure out which sequence of control actions will ultimately minimize the difference between the state of your system and where you want that state to be. And there could be other constraints that you want that path to be fairly smooth, etc. So you get all those problems of constraints again. Again, it's a minimization problem, and here, unlike in the first two cases of minimizing the prediction error or optimizing a function, each iteration is actually executed, and the response of a system rather than a function calculated abstractly is what you're dealing with. So an actual control system will make a change, see what the output is, and make another change. Again, techniques like gradient descent, Newton's method, and all that start applying, but now you're controlling actions. So from predicting the future or predicting where things are going to go, to figuring out how to best utilize that information to optimize one's own goals, and then to decide how to change one's behavior or change one's system so as to get to the goal state. All these are tightly related. And I hope you've seen that the mathematics is related. Now let's talk about some of the applications. Before we do that, of course, in practice, whether you're dealing with support vector machines, logistic regression, neural networks, or what have you, you won't ever really have to do these things. There are packages available that let you choose, let you apply any of these techniques without having to get into the math or get into the iteration. The important thing is, of course, trying to choose which package to use, and as soon as we do the applications, I'll try to summarize which package to use, what kind of techniques to use from my experience, and then we move on to other topics such as deep belief networks.